Welcome to The Explainer. Today, we're cracking open the legendary Attention is All You Need paper to get at one single brilliant idea that really changed everything for modern AI. And that idea is all about a simple question. How do you teach a machine the concept of order? So let's just jump right in with this central puzzle. This is the paradox the creators of the Transformer were facing. They built this architecture for incredible speed, but that speed came with a huge catch. The model had absolutely no built-in sense of which word came first. All right, section 1, a model without order. See, the whole point of the Transformer was to break free from what came before. Older models, like RNNs, had to read a sentence one word at a time, just like we do. But for a computer, that's a massive bottleneck. It's just too slow. And the paper says it right there. They wanted to get rid of that one-by-one limitation entirely. By throwing out what's called recurrence, the model could suddenly gulp down an entire sentence in one single bow. This is what we mean by parallelization, and it's what made the Transformer so incredibly fast and powerful. But wait a minute. This creates a huge problem. Look at these two sentences. The dog chased the cat chased the dog. We're using the exact same words, right? But the meaning is totally different. If the model just sees a jumble of words all at once, how in the world is it supposed to know who was chasing who? So there it is. This incredible superpower of seeing everything at once came with a potentially fatal flaw. The model was completely blind to sequence, which is, kind of the entire basis of language and meaning. So how did they solve this? Well, this brings us to section 2, the positional encoding fix. And the solution they came up with is just so elegant. Instead of forcing the model to slow down and read word by word, they just gave each word a little tag, a sort of mathematical fingerprint that tells the model exactly where it is in the sentence. And the magic happens right at the very start of the process. Before the model does any real work, this positional encoding signal gets added directly to the word's embedding. That's its initial meaning. It's like stamping every word with its home address before it even enters the assembly line. So what is this thing, really? It's a vector, which is just a fancy word for a list of numbers. But the key is that this specific list of numbers provides a totally unique signature for each and every position in a sentence. Okay, this is where it gets really interesting. How do you actually create this unique signature? Let's dive into section 3, decoding the formula. Now, you might think you just count 1, 2, 3, 4. But they did something way, way cooler. They used waves, specifically sine and cosine wave. Now I know these formulas look a little intimidating, but don't worry, it all boils down to just 3 key ingredients. And once you see what they are, the whole thing actually makes a lot of sense. Let's break it down. First up, you've got pause. This is the easy one. It's literally just the position of the word in the sentence. The first word is at position 0, the second is at 1, the third is at 2. Simple as that. Next is demodel. So to an AI, every word is represented by a long list of numbers that captures its meaning. Demodel is just how long that list is. For the original Transformer, every single word was turned into a list of 512 numbers. And finally, we have I. So if our list is 512 numbers long, I is just a counter that lets us calculate a value for each of those 512 slots. It helps us generate a different part of the wave pattern for every single spot in our position vector. So we have the word's position, the length of the vector, and a counter. How do these create that unique fingerprint? Well, that brings us to section 4, a unique frequency signature. And this is where the intuition behind using waves really shines. Here's the best way to think about it. Imagine the positional encoding for each word is a unique musical chord. Each of those 512 dimensions is a different note or a different wave. The formula uses that counter, I, to create 512 waves, each with a slightly different frequency. The final position, fingerprint, is that unique chord made of all those waves playing together. What's so clever is that some of these waves are very long and slow. These give the model a general sense of location, like, is this word near the beginning or the end? But other waves are super fast and high frequency, and those give the model a very precise, fine-grained location. It's the unique combination of all these different waves that gives every single position its own unmistakable signature. So this obviously begs the question. Let's get into it in our next section. Why sines and cosines? I mean, Of all the things in mathematics, why this particular pair of functions? There has to be a pretty good reason for all this complexity, right? Yeah, exactly. Why this specific pairing? It turns out this was no accident. The choice to use sine and cosine together unlocks a kind of hidden superpower that is absolutely essential for the model to learn. The paper gives us the answer directly, basically, and this is the key insight. Because of the properties of these waves, the signal for a word, say 3 steps down the line, can be calculated as a simple, consistent transformation of the current word signal. The relationship between position 5 and position 8 is mathematically identical to the relationship between position 15 and position 18. It creates a perfect, consistent ruler. And why is that so important? Because it means the model doesn't just learn this word is at position 5. It can easily learn the relationship between positions. It can learn the concept of 3 steps forward or 2 steps back. This ability to understand relative distance is what allows the attention mechanism to figure out grammar and how words influence each other no matter where they are in the sentence. And that brings us full circle to our final section, restoring order to AI. By baking this incredibly clever mathematical signal into the inputs from the very start, the transformer gets to have the best of both worlds. It gets to read everything at once, making it unbelievably fast and efficient. But thanks to this wave-based signal, it never, ever loses track of the original order of the words. Information about both what a word means and where it belongs flows through the entire system together. And that's really the punchline. This was a simple, elegant mathematical trick that the model doesn't even have to learn. It's just built in. It solved the fundamental problem of order without adding extra complexity, which freed up the powerful attention mechanism to focus on what it does best: understanding relationships. It's what allowed attention to truly be all you need. It's just such a powerful idea when you think about it, that something as abstract and human as sequence or order can be perfectly captured by this elegant pattern of waves. It really makes you wonder, doesn't it? What other complex ideas are just out there, waiting, not for a bigger data set, but for someone to discover this simple, elegant equation that defines them?